What? Okay. All right, so we're attempting to have class, and we'll see how it goes. But as you see, we're kind of doing a Harry Potter theme. Um, so, and
Can I theme every class?
Please.
Can we dress up for
them?
Well,
He said, please don't. He just like shot that down. I didn't ask you anyway.
let's
Okay.
I'm open to it. So,
Okay.
okay.
If you draw something, I'll dress up.
I apologize.
Okay.
I love drawing.
No, you don't. Did you hear him? He just like totally
Actually,
shut
I might have
down.
trouble writing on the board, not so much because of this stuff, but because of the stuff that was left here before.
See, it's not my fault anyway.
Yeah, well, we'll see how it shows up.
Or is the Deathly Hallows thing? I don't like that.
Okay. Well, definitely try to leave yellow stuff up.
Yeah.
Um,
Well, that pink went away easily. Give it a little more.
okay. Alright, so still talking about the fundamental matrix and the flow for linear systems. Well, linear systems is all we've been doing in this chapter anyway. Now, where I left off last time was that the determinant of the fundamental matrix is guaranteed to be non-zero, because I derived what's called Liouville's formula that shows that the determinant is actually the exponential of something, so it can never be zero. All right. So now we have that g of t inverse exists. That's something we can take advantage of. So what I'm going to do is, if we look at a general non-homogeneous linear system, so x prime is a of t x plus b of t. And now that we have an inverse, actually I'm going to write this a little differently. I'm going to move the first term to the other side and write it like that. And then what I'll do is we'll multiply both sides by G inverse. And keeping in mind, I want to keep in mind as I do this, G and A are both functions of t, but just to keep things abbreviated, I'm going to not write any actual t dependence, just because I have a lot of steps to go through. Okay, so G inverse B, and B also has t dependence. Okay, now the next thing I'm going to do is I'm going to, in here, multiply by G and G inverse, which just, because that cancels out, so it doesn't change anything. So basically, it's a matrix version of a multiply and divide trick. And the reason I'm going to do that is one of the properties of the fundamental matrix is that this right here is equal to G prime. Okay, so AG condenses to G prime, and that should be an X prime right there. Now, so now we have minus G inverse G prime G inverse. Now, how is that helpful? So under the one here, we give you a very important formula that's useful in a lot of contexts. That's going to help us here. What is the derivative of the inverse of a matrix? Actually, we're working with G. So I'll just use that letter there. Because if you know the derivative of G, what about the derivative of the inverse? Well, in the n equals 1 case, so we're just doing a plain old function rather than a matrix. What's the derivative of 1 over x? Yeah. You want the other way.
Well, yeah, that's how it
Yeah, so minus 1 over g squared g prime. So that's for n equals 1 case. So the formula we get in the matrix case should be consistent with that. So to get the inverse, we're going to use the fact that g times g inverse is identity. So now we're going to differentiate both sides of that. Of course, the derivative of identity is 0. So how do we differentiate this? We use the product rule. Now, product rule for matrices is exactly the same as the product rule for regular functions. You just have to be careful about the order. Matrix multiplication, the order matters. So what we get is g prime, g inverse, plus g inverse prime is 0. So product rule works the same in that in each term, one item is differentiated. This is to make sure that whatever order we had here, g and g inverse, we have g and g inverse, g and g inverse. So keep the order the same, and the product rule works out just fine. Okay, so now all I have to do is solve this equation for g inverse prime. So what you can do is I can take, this is what I want. So I'm going to take this term and move it to the other side. So I have a minus g prime g inverse. But this is multiplied by g, so I multiply both sides by g inverse to move this to the other side. But I have to multiply on the left. So we have a g inverse on the left. So if you compare this with this, you see they're at least consistent with one another. Because over here we have two g's in denominator. Here we have two g inverses. We just have to be careful about the order of multiplication, and then it all works out. All right. So now, if we go back to a formula that we had here, okay, so I'm going to rewrite this as, okay, g inverse x prime minus, okay, so ag is g prime. So I have minus g inverse g prime g inverse x is equal to g inverse b. So what do we have? Minus g inverse g prime g inverse. That's exactly what I have over there. So this is plus g inverse prime. What?
Oh, I was laughing at him moving. Sorry.
Okay. All right. Oh gosh, in fact, the meeting Friday, just shoot me now.
And that's on video.
Not just me. You can't edit that out. I mean, you can, but you shouldn't.
Well, I think only students are going to see it anyway. Anyway.
Posted on YouTube, right?
What?
Posted on YouTube, right?
Yes, publicly. Yeah, but who's going to bother looking for it? You guys and the one other student who's not here.
Mm-hmm.
So, okay. So I'm not too worried. Okay, and unlike last time, I need to not forget to move over. Yeah. Okay. So I can try to work around the other Harry Potter decoration.
So did you do the, you're doing plus g prime there? inverse prime.
Yeah, because the derivative formula has a minus in it.
So what you're saying is you're replacing that with plus G prime and G inverse prime.
Yes.
Right.
Okay, so to clarify, we have, G inverse x prime plus G inverse prime x equals G inverse b. So that's where we're at now. But look at what we have on the left side.
Product rule.
Yes, it's a product rule because in each term, they both have a G inverse, they both have an x, and each term only, that's an x prime, to see the product rule, only one item is differentiated. So we can condense this to
G inverse X.
G inverse x, the whole thing prime, equals G inverse b. Okay. So now what I can do is integrate both sides with respect to, I don't want to integrate with respect to t because I need t as a limit. So I have integral from 0 to t of G inverse, G of s inverse x of s prime ds is integral from 0 to t G of s inverse b of s ds. Okay. Now on the left side, the integral cancels the derivative. So I have g of t x of t, which is what I'm after in my solution, minus inverse. And then I have g of 0 inverse x of 0 equals that. There's no need, I'm not going to do anything with that, so there's no need to write it again. Now, fundamental matrix. What is g of 0? It's identity. So that goes out. So now I can take this term that just has x of 0 and move it to the other side. And then I can multiply by g of t on both sides to cancel out the inverse, thereby solving for x of t. So x of t is g of t x of 0 plus g of t again, integral from 0 to t, g of s inverse b of s ds. So this is the formula for the solution of a non-homogeneous linear system, all expressed in terms of the fundamental matrix. And in the notes and in the book, there is we basically just derived it right here. So if you want, you can take that as a proof. But they go ahead and prove it again anyway by just taking this and taking a derivative of x and showing that the derivative of this really does satisfy the system. So I won't go through that now because already so much time has been wasted. Okay. All right. Let's see. Is there any questions about how this was derived? All right. Now we can talk about the flow. So Dr. Tian covered the flow map for nonlinear systems in Chapter 3. So now we can specialize as linear systems where things simplify quite a bit due to the linearity. Okay. Let's see. I don't know if I can use all of this blank space on the board. That is not potterized. Okay, yeah, before I move back to the other side of the board. Okay. Although, yeah, this other stuff was not erased well at all. by. So think of your superscript as your starting time, and your subscript as your ending time, and x is your initial data, is given by alpha t, where alpha t is a solution of your initial value problem. Whatever linear, nonlinear initial value problem that you have, with the initial condition that x of alpha of s is equal to x. So flow map is what takes this initial data that's given at time s and gives you what the solution is at time t. That's really all the flow means. But if you have an explicit solution formula like this one right here, you can just use that to express flow. So what you can do is, okay.
Does anyone have an extra pen or pencil?
Oh, what happened to yours?
In this round.
Oh, okay.
It's pink.
It's perfect. Okay.
Yeah, your pink pen stopped working the other day, doesn't it?
Oh, I have. Well, no, this one's my pink pencil.
Sorry about that.
Okay. Because so keep in mind that hold on. There's certain things I'm trying to skip over, but I want to make everything still yes. Thank you. Okay. Now, right. Okay. So the thing is, if alpha of s is equal to s, then our solution formula uses alpha of 0. So here's what we can do. I can use that solution formula with time s instead of time t. So I'll have g of s, and then I have some, so my unknown here is alpha of 0. And then I have plus g of s integral from 0 to s. Now, I need to use a different letter inside the integral. So I'll just use a u. Okay. And what I can do then is I go ahead and solve this equation for alpha of 0. So I can take this term and move it to the other side, and then I can multiply both sides by g of s inverse. So I get alpha of 0 is equal to g of s inverse x minus integral from 0 to s g inverse of u d of u du. Okay.
The G of S and the G inverse cancel out, right?
Well, yeah, this multiplying by g inverse to isolate this cancels out this g inverse over here. Yeah, so that's why there isn't any g out front in the integral. So now what I can do is, if I want to solve for the flow, so the flow is, I can go ahead and you plug in alpha t. So I have this solution formula. G of t times this x of 0. So my initial value is what I'll plug in here. So alpha of 0 is what goes in here. But I still have that other term, plus g of t integral from 0 to t, g of s inverse, actually I'm going to use the same letter. Okay. So now what I'd like to be able to do is condense all of this. Because if I look at my integrals, I have the integral from 0 to t minus the integral from 0 to s. Now what I can do is I can flip the limits on this integral, provided I change the sign. So if I'm adding the integral from s to 0 to the integral from 0 to t, that condenses to what integral? S to t. Just using basic properties of definite integrals. So the flow is g of t, g of s inverse x plus g of t integral from s to t of g of u inverse b of u du. Okay, so that's the formula for a flow. So it's kind of like what we're doing here is, in a sense, we're taking our initial value x and we're backing it up to time 0 and then starting again and going back to time t. So if you want, you really could look at it that way. And then a similar thing happens to the integral, like taking the integral from s back to 0 and then going from 0 to t is the same thing as going from s to t directly. All right. So there's not much, so really it's that exact formula, but just working with a different initial time. That's really all there is to it. Okay. Okay. And if we focus just on this term here, that is the flow for the homogeneous case, where it's just x prime is equal to a of tx, just because in that system b is 0, so you're just not going to have this integral term here. Okay. So any questions about what happened here?
Would you add that plus gt 0t?
Oh, I'm sorry, what?
Could you repeat that second to last step?
Oh, from here to here?
Yeah.
Okay, so since both these integrals have multiplied by g of t, so I can try combining the integrals. So basically I'm chaining together s to 0 to t is just from s to t.
Yeah. I get that, but I don't get where did that integral pop up.
Oh, where did this integral pop up? Okay, I took this whole expression for alpha of 0 and plugged it in here
Oh.
for x of 0,
Yeah.
and then I still had that.
Oh yeah.
Okay.
X of t is the flow
Um,
from that formula. X of t is the flow.
Well, so the thing is, it's all a perspective thing. What the flow does is say, here is a solution at time t given some sort of previous data at time s.
Right.
Since it's still a solution, there's really not really any underlying difference between what the flow is, what the explicit solution formula is.
Right. So
Yeah.
that's alpha t, right? Because alpha t
yeah.
is the solution of the IVP, which is.
Yeah.
Yeah.
Yeah, because the explicit formula here is expressed in terms of time 0, but what I could have done was expressed it as starting at any time, and really that's what I've done here. Okay. Okay. Let's see, have a example here. Oh. Dang it. Oh. Not sure what this is doing here. Don't lose that. Okay. Okay, so we have this system as an example. Here's our system matrix. Now, last class, I used this as an example where the fundamental matrix turns out to be e to the minus t cosine of t squared on the diagonal, and then t squared minus sine t squared. Okay. So if you have a 2 by 2 matrix, you have an explicit formula for the inverse. So that is 1 over the determinant. And then we switch the diagonal entries and negate the off-diagonal entries. Okay. So now we can go ahead and use that to write down the inverse. Now, when the matrix is multiplied by a constant, actually, I'm going to use S here. When the matrix is multiplied by a constant, the inverse is multiplied by 1 over that constant. So that's e to the s. And then we have the diagonal entries. And then we negate the off-diagonal entries. Okay. All right, so then what we can do is go ahead and multiply these out for defining a flow. So g of t times g of s inverse. Now, so by multiplying these, we get e to the s minus t. And then what you have to do is carry out the matrix multiplication. Now, yes?
Why is it just e to the s and not e to the negative?
Oh, that's what I was saying earlier. If the matrix is multiplied by like a single entry, like basically a scalar, then the inverse is multiplied by 1 over that. Okay. So now if you carry out the multiplication, what will happen is, for instance, in a 1, 1 entry, you would get cosine t squared, cosine s squared, plus sine t squared, sine s squared. So you have cosines times each other, and sines times each other, or sine times cosine. The point is, and I won't do the whole thing out here, when you multiply these out, you can use a lot of trig identities, the sum and difference formulas for sine and cosine. And that allows you to write this in a condensed form. So it turns out to be cosine of t squared minus s squared on the diagonal. And then we have sine t squared minus s squared up top, and then minus sine down below. Okay, so this is using the formulas for cosine and sine. because when you multiply this times this regular matrix multiplication, you actually get expressions of this form, either this on the diagonal or this on the off diagonal. So then you condense them using these identities to get these guys. Okay. So then what you can do for the flow is, okay. So that means that the flow for the homogeneous system, so x prime is equal to a of tx, is just going to be equal to that matrix. So it's going to be g of t, g of s inverse times a vector x1, x2, which is x. There's two components. So it's just going to be e to the s minus t times all this. Times x1, x2. So you're going to have matrix vector multiplication for that. But then the question is, what happens, therefore, to the flow as t goes to infinity? Well, cosine and sine are just going to keep oscillating forever, so nothing interesting is going to happen there. What about the exponential? What's going to happen to that as t goes to infinity? Yeah, because it's e to the s minus t. So,
Negative infinity, equal to 0, right?
yeah, so it goes to 0 as t goes to infinity. So what that means is all integral curves converge to the origin. So it doesn't matter where you start from or at what time, your integral curve is eventually going to go to the origin. And it's going to oscillate around because of the cosines and sines here. So in fact, if you actually were to trace out integral curves, and this is done in the book, they spiral around and towards they spiral inward towards the origin. Okay. All right. Now that's for the homogeneous system. X prime is equal to just a of t times x. So then, what about a non-homogeneous system? What kind of behavior are we going to get from that? So for a non-homogeneous case, we'll have x1 prime is minus x1 plus 2t x2. And then we add on a non-homogeneous term, sine of t squared. And x2 prime is minus 2t x1 plus minus x2 plus cosine of t squared. Okay, so in the matrix vector form, this is x prime is a of t x plus b of t. So A is the same matrix as before, minus 1, 2t, minus 2t, minus 1, and then b is sine t squared cosine t squared. Okay. So the thing is, the way we can express the solution of this is, okay, so we have the solution formula. X of t is g of t x of 0 plus g of t integral 0 to t g of s inverse b of s ds. And this right here is, I'll call that xh of t. And this part here is xp of t. And so these solve different problems. So xh is a solution of a homogeneous system. X prime is a of tx. And with the initial condition, okay, actually, I'm just going to call the initial condition C. Okay. So that's basically a general solution of a homogeneous problem. And then xp is a particular solution of the non-homogeneous system with b of t added in, and then the initial condition is 0. So basically we're just decomposing the solution into two parts. You probably would have seen that in your first DE class where you'd have homogeneous solution plus particular solution. Okay. Now, these major C's that we have g of t here, we know what that is. And we have g of t times g of s. So we know what that is too. Because we can take this g of t, it's like we can move it inside the integral if we want. It's kind of like I could take a constant, you can move it in, you can move it out. So that puts me in a position to write down both parts of the solution. So I'll go ahead and do that now. Okay. Okay, so the whole solution, so xh of t is just g of t times c. So that is e to the minus t, and we get cosine t squared sine t squared. Yep. Minus sine t squared cosine t squared times the initial value, which is just c1, c2, whatever that is. But because of the negative exponent, we know what this does. This goes to 0. The t goes to infinity. So that's like the non-interesting part of the solution. Okay. Now what about the particular solution? So that is the integral from 0 to t of g of t, g of s inverse, b of s ds. Now, g of t, g of s inverse, I have that written down over there. So we go ahead and do that. So that's e to the s minus t cosine t squared minus s squared. Oh, actually, you know what? No, I don't want to do that. If I carry out the multiplication, even though I have the result written down over there, it just makes things harder later. So I'm going to move a g of t back outside. Sorry about that. Thought I could save myself some time, but no. Okay, so if it's write out what everything is, so I have, okay, e to the minus t cosine, get really tired of writing cosine t squared and or sine t squared. Okay, times the integral of e to the s, and we get cosine s squared minus sine s squared, sine s squared cosine s squared, times b of s, which is sine s squared cosine s squared ds. Okay, so now when we go to work this out, we carry out matrix vector multiplication. So here I have cosine times sine minus sine times cosine. So the first entry of this matrix vector product is just going to be 0. Everything will cancel out. And then for the second component, I have across the second row and down this column, sine squared plus cosine squared is just going to give me 1. So that simplifies quite a bit. So now I have, I'm just going to write g of t because I'm tired of writing it. Integral of 0 and e to the s ds. So then you go ahead and work out that integral, and you get 0, and then you get e to the s, or e to the t minus 1. So now you get to multiply all that by g of t, and you have that exponential. So this just turns out to be e to the minus t times this, so that's 1 minus e to the minus t times, okay, and because we have a 0 down here, then we're just going to end up taking the second column of this matrix. So minus sine of, second column of this matrix, sine of t squared, cosine t squared. So if you carry out, once again, the matrix vector multiplication, this is what you're going to get. So, so this is your particular solution. Now, as t moves forward, if we just focus on this vector part here with sine t squared, cosine t squared.
How did you get 1 minus e to the negative t?
Oh, this times that.
Right.
Okay. You have a question?
The second column of that guy, which is
Is second column this? Yeah.
column multiplication, so it's negative sine t squared.
Oh, there's no negative there. Yeah, it's this.
Right.
Yeah, because when you multiply the right by a vector, you multiply this by 0, 1. The 1 takes the second column, and then the 0 excludes the first column. Okay. We good? Or your brains are all fried anyway? And you have one more class to sit through? Probably taught by an angry professor. Just got busted.
Thanks to you.
Yeah. Great. Yeah, that's going to happen to somebody. Okay. Now, just if we just look at this part, we'll see the behavior again as t goes to infinity. So here, what's happening to this as t marches forward? If it's like a x coordinate is a sine and y coordinate is a corresponding cosine, how's that going to behave? So if you have an x-y pair, sine theta, cosine theta, whatever theta is, as t is going forward, what kind of path is that going to trace out? Yes, it's going to be a circle. In this case, the unit circle, just this part. Now, what about this over here?
1.
Yes, because e to the minus t is going to go to 0. So this whole thing converges to the unit circle as t goes to infinity. So the particular solution goes to the unit circle. The homogeneous solution converges to the origin. So if you just put the two together, so the entire solution converges to r equals 1, the unit circle in polar coordinates. And also it doesn't matter what the initial data is. Okay. Now, I should emphasize though that a key driving force in this behavior is the choice of non-homogeneous term, sine t squared, cosine t squared. So you can think of it as like extra initial data that's being added at every instant that causes this convergence to the circle. Now, if I had chosen a different vector there, we would have gotten altogether different behavior. The initial condition ends up not mattering just because the homogeneous solution is going to go to 0 no matter what the initial data is. But for a different matrix, like for instance, if these entries, like a -1 here, if they had been positive, that would have caused very different behavior. Instead of spiraling inward, it would have spiraled outward. So there's all kinds of different behaviors that you can get. This is just
Would be a hyperbolic sine and cosine.
Possibly. Well, it depends on the singular entries of a matrix, but yeah, because if you have those exponentials like that, positive, or maybe if you have a combination of positive and negative exponential, like if you have a 1 and a -1, then in that case you can get it depends on a lot of things, but it's possible to get hyperbolic functions because you're getting a linear combination of e to the t and e to the minus t.
So the homogeneous particle goes to 0 regardless, and then
Yeah,
the
the particular solution is just going to go to the circle, and then so this is like some parasitic part is just going to go away. Yeah. Okay. Now, I still have some time left, not a whole lot. But during the rest of the time, and then whatever time I need on Wednesday, talk about a special case. So we've already specialized down to linear systems, and now we specialize further to constant coefficient systems. And things get particularly nice there. And I found that this, especially in this chapter, this book, does a really good job of beating a dead horse. So I'm going to try not to do that, because otherwise we could easily spend forever on a single section. What?
It should be confusing. I didn't hear it.
Sarah Jessica Parker.
Okay.
Oh.
She has a hard speech, right?
What?
Oh my
So
god.
that you're saying she looks like a horse?
And then in South Park it gets,
Yeah.
Oh,
oh my god.
okay.
Yeah.
Oh my god.
South Park.
Wow. Okay. So I'm missing some lovely South Park reference here.
Okay.
Okay.
Man.
That's how I got introduced to Sarah Jessica Parker.
Through South Park.
Not
Through
really,
South
but
Park?
Yeah. No,
Interesting.
through the internet.
Okay.
Pictures of horses. I'm like,
Oh my god.
Oh god.
Okay then. So, well, I guess that's some searching we can do after class. Alright, so homogeneous constant coefficient systems. Okay, so what happens here is it's actually not all that interesting to try to show that that if A of T is just a constant matrix, then your fundamental matrix is nothing more than the matrix exponential. Now I need to give a definition for that, but that's easy enough to define in terms of the Taylor series or Maclaurin series for the exponential. So just in terms of taking powers of a matrix instead of a number. Okay. As a result, so here's some formulas for you. Okay, so the explicit formula for a solution of a, oh, wait a minute. Okay. I actually care about more than just, let's strike the homogeneous, but we'll just do the constant coefficient whether it's homogeneous or not. So the solution formula is just specializing from what I wrote down earlier for a more general linear case. That's going to be e to the at times the initial value plus integral from 0 to t e to the a times t minus s, d of s ds. And the reason for that is g of s inverse is e to the at, e to the as inverse. But to take the inverse of that, well, what's 1 over e to the x? It's e to the minus x. So all you have to do is negate the exponent. And in the solution formula, you have e to the at outside and e to the minus as inside. Well, you can just go ahead and combine them. So that's what leads to this formula here. Using similar manipulations as in the last section, the flow would be, so you're starting at time u and ending at time t. So it's e to the a times t minus u x plus the integral from u to t of the same thing. Okay, so you can infer all of this directly from the formulas that I already gave for the non-constant coefficient case. I mean, you can use effective when you fill in that the fundamental matrix is e to the at, and we can see what the inverse is right here. You can see how you can just condense everything and get these simpler formulas.
So in the second integral, you chose t minus s because the initial time was s. E to the a times t minus s. The second, yes.
Yeah, well, it's the same thing as going on here. You have an e to the at out here, and then an e to the minus as in here.
So you're going to combine those two terms.
Yes, you combine them.
Okay.
Okay. And the this is specializing from more general systems. The flow map satisfies the semi-group property that Dr. Tian talked about before. And so now what happens is that same semi-group property is observed here too. Now in the homogeneous case, I can say a little more about the flow. So we just have that first term there. So it's e to the a t minus u x. But really what we can do is simplify it down to just one parameter. Because it only depends on the difference between times. So it's just e to the at x. Where t is now, it's not the absolute value that time matters, but just how far in time you're going. It's a time span. So it's the difference between your initial time and your final time, wherever those times may be. Okay. In a homogeneous case only, all these flow maps, they have more than just a semi-group property. They actually form an abelian group. Because you have all the properties of a group that a group should have. Closure, identity, inverse, associativity, everything is satisfied. You have that. Plus you have commutativity because e to the at, e to the st is equal to, no, e to the as is e to the a s plus t, but you can break that apart again as e to the a s, e to the a t. So that shows it's an abelian group. So we have an even nicer algebraic structure for a flow map in the homogeneous case compared to the non-homogeneous one. Okay. Do I have any time left? No. It's exactly the end. Okay, that worked out well. All I have left is one example, and I'll quickly fit that in on Wednesday. Then we'll get into more hellacious stuff. Okay. Well, what a very pottery class. But yeah, I'm surprised it wasn't all that hard to work around everything.
Wait till Wednesday.
And now we'll see if I hear from Dr. Ding at all.